Hello, welcome. Today we are going to be looking at magnetic flux and the Earth magnetic field. Magnetic flux is defined as the surface integral of the normal component of the magnetic field passing through a surface. If the magnetic field is constant, the magnetic flux passing through a surface of a vector area S is given by B dot S or Bs cos theta, where the heavy Bs is vectors and the light Bs is scalar, where B is the magnitude of the magnetic field, the magnetic flux density, having the unit of Weber per meter squared or Tesla. S is the area of the surface, and theta is the angle between the magnetic field lines and the normal perpendicular to S. Now, the Earth magnetic field that tends to keep a freely suspended magnet in the north-south pole direction is the Earth's magnetic field. That very field that tends to keep a freely suspended magnet in the north-south direction is the Earth's magnetic field. This field behaves as if there is a short magnetic bar in it which is inclined at an angle to the axis of rotation, with the north pole pointing south and the south pole pointing to the northern hemisphere. So from this we can deduce that the field that tends to keep a freely suspended magnet in the north to south direction is the Earth's magnetic field. And we also know that magnetic flux is the surface integral of the normal component of the magnetic field passing through a surface. Now we look at, so this is actually the diagram of what we just explained now. This is the diagram. So this is the Earth. This is the Earth. And you can see the Earth's magnetic field as if there was a magnet that is kept, you understand, freely in north-south direction. So this is the actual Earth. This is the geographical North Pole and geographical South Pole. This is the magnetic field that we're talking about. You can see it. See the movement north to south. You can see. So this is Earth's magnetic field. Now we look at magnetic declination or variation. That is changes in magnetic field from place to place. So magnetic declination or variation is the angle between the magnetic and geographical meridians. So that very angle, you can see it here in this diagram. This is the geographical meridian, whereas this is the magnetic meridian. That very angle in between the geographical meridian and the normal meridian or magnetic meridian is known as magnetic declination or variation. So magnetic declination or variation is the angle between the magnetic and geographical meridians at the place concerned. It varies from place to place and with time. It points at places with no declination. Okay, points at places with no declination are known as agonic points. So those points are places with no declination, places where the geographical meridian and magnetic meridian are equal or does not produce any line. We call them agonic points. Now, forces between two parallels When currents flow through two parallel conductors, see this conductor, see this, of a given length, either in the same or opposite direction, it produces two things. One, a magnetic field around the conductors, and two, a force between the two conductors. So whenever you have current flowing through, this is a conductor, this is another conductor, they are in parallel. So you see current flowing through them, either in the same direction. This is a conductor, this is a conductor, flowing in the same direction. This is a conductor, this is a conductor, flowing in opposite direction. Two things must happen, provided they are of the same length. Now, a magnetic field around the conductors, there will be, you can see this magnetic field around these conductors, and a force between the two conductors. There's also force between the two conductors. Now, moving coil and moving instrument, iron instrument. If an electric current is passed through metal conductor of length L, placed at right angle to a strong magnetic field B, this is the metal conductor, electric current is passing through it, and is placed at right angle to a magnetic field B, the conductor would be observed to experience a force. This conductor will be observed to experience a force perpendicular to it in accordance with Fleming's left-hand rule. So this a moving coil or moving instrument that has current passing through it and is placed perpendicular to a magnetic field always has force acting perpendicular to it in accordance to Fleming's left-hand rule. So take note. Now we look at deflection path of a charge. If a positive charge Q enters a magnetic field at 90 degrees, if a positive charge Q enters a magnetic field at 90 degrees, the charge is deflected in a circular path. The charge is deflected in a circular path by a force that acts perpendicular to it in line with Fleming's rule. So this charge is deflected in circular path by this force that acts in line with Fleming's right hand rule. Very important. So that is what is actually happening here. See, charge moving. There is force acting on it in a circular path. So that is what, because of deflection. Now, moving iron instruments, moving iron ammeter. The magnetic effect of electric current in a solenoid is utilized in taking current reading from a moving iron ammeter. That's one of the applications of the magnetic effect of electric current. This type of device consists of a solenoid in between a fixed soft iron piece, a movable soft iron, a non-uniform scale on which moves a pointer, a spring to control the angular deflection of the pointer. So this is the arrangement of a moving iron ammeter. So what are the advantages of a moving iron ammeter? It can be used to measure DC and AC. So you can use it to measure both DC, that is direct current, and alternating current. What are the disadvantages? The reading scale is not uniform. This can be corrected by calibrating a new uniform scale by ensuring that the soft irons are specially shaped and tested. So that's how you take care of the disadvantage of not having a uniform scale for a moving iron ammeter. Conversion of galvanometers to ammeter and voltmeter. In subsequent classes, we are going to go into details on this. But conversion of a millimeter galvanometer to an ammeter. To make a galvanometer or milliammeter read current in ammeter, a low resistance called the shunt is connected to in parallel with the meter. By so doing, most of the current to be measured go through the shunt, while a small amount passes through the meter. So this is the low resistance connected, and this is the shunt. So most of the current passes through here. Lesser current pass through here. Assuming a full scale deflection of a moving coil ammeter of internal resistance, this is this, and it is required to measure a current of this. Then the current passing through the shunt is 1 minus this. So most current pass through the shunt. So that is this 0 point this. So in shunt is parallel to this. So I have this calculated, which we'll do much in details in the next class. A conversion of galvanometer to voltmeter. To convert a milliammeter or galvanometer to a voltmeter, a high resistance shunt. You see, in the other one for ammeter, a low resistance, but this one a high resistance shunt called a multiplier is connected in series. The other one is in series with the meter. For example, if a milliammeter is to measure a PD across a bulb, the meter is connected in parallel. Assuming the galvanometer of internal resistance, this is an example of calculation which we are not doing now. Subsequent classes will do it so that we can understand it better. So those are the things that we are doing here. So in subsequent classes we'll do more on this. Please, if you like this video, hit the subscribe button by this side of the video. If you have any question, drop it on the comment section. If you want to support us in any way, please check the description section and you see our contact so that you get to us. If you want to collaborate with us in any way, also do same. Thank you and God bless.